All right, so with the final section of this chapter, we're going to look at gravimetric analysis. And essentially what this is changing a substance so that we can kind of identify one portion of it and then do a series of calculations. So we're going to see a couple of different kind of methods, and one of them is going to be something we've already talked about. So with a precipitate, for instance, we can have a precipitation reaction occur, collect that precipitate, get the mass of it, and then based on the mass of that precipitate, we can identify the portion of a sample, of a previous sample that contained whatever that substance may be. So if you think about it, in this case, we've got a original sample with a mass of 0.4550 grams, and then some amount of that sample is magnesium sulfate. So we're going to take that sample and dissolve it in water and then just react it with a whole bunch of barium nitrate. And then in this process, we're going to have the magnesium sulfate, we're going to have the barium nitrate combined to form a precipitate of the barium sulfate. And then based on the stoichiometry, based on the mass of this barium sulfate, we're going to be able to back calculate the original mass of the magnesium sulfate in that sample. So with this one, if we look at it again, we've got the original mass of the magnesium sulfate, and then again, it's telling us excess barium nitrate. So one way we could assure ourselves that there's excess is we could assume all of this original sample is magnesium sulfate. We could then figure out how much barium nitrate do we need to react with that, and then just add a little bit more even there, just to be absolutely certain. But then we have this reaction take place. We collect our precipitate, just like we saw in the previous slide. We could just do a simple filter in order to drain the liquid, allow it to dry, get the mass, and we determine the mass of the barium sulfate precipitate is going to be 0.6168 grams. So now we've got the mass of the barium sulfate. We want to ultimately determine the mass of the original magnesium sulfate. So it's just going to be the stoichiometry. Ultimately, we're trying to get the mass percent, but in order for that, we need to get the mass itself. So we can use 0.6168 grams of barium sulfate. We can use the molar mass of barium sulfate. We can then use the mole-mole ratio, 1:1. And then finally, we can use the molar mass of magnesium sulfate. So if we see those steps drawn out here, so again, starting with grams of that substance, we'll use the molar mass with grams on the bottom, converts to moles of barium sulfate in this case, 1:1 for the mole-to-mole ratio because the coefficients in that balanced chemical equation were 1:1. And then finally, we're using the molar mass in this case of magnesium sulfate. So that's why it's 120.37 rather than 233.43. If we were to use the molar mass of barium sulfate again, we'd essentially just be undoing what we've already done. So we want to make sure we're using the molar mass of that second substance. And in this case, that tells us there was 0.3181 grams of magnesium sulfate in that original sample. But we weren't just interested in the mass of that magnesium sulfate. We wanted to figure out of that original sample, the mass percentage that was magnesium sulfate. So we've got the entire sample. We've got the portion that's just magnesium sulfate. So we're going to be able to divide those two, part over whole. So in this case, the magnesium sulfate over the entire sample, multiply by 100 to make it a percentage, and we're going to get just a smidge under 70%. And then again, we've got 4 sig figs in both of these values. So that's why we've got 4 sig figs in that percentage. And then in addition to precipitation reactions, we can use a combustion reaction and then what's known as combustion analysis in order to determine in a sample, particularly with a hydrocarbon. Could also do it if it's like a hydrocarbon that also, or it wouldn't technically be a hydrocarbon, but a carbon, hydrogen, oxygen compound. You can do it with similar ones. But essentially what we're going to do is have this combustion reaction take place, produce the products like carbon dioxide and water, and then we're going to have specific sort of chambers that are going to collect or going to essentially absorb those different gases. we can then measure the mass of the gases, and then based on the mass of the carbon, based on the mass of the hydrogen, we can figure out the percent composition. We can get the empirical formula of these hydrocarbons. So like I said, with a hydrocarbon, we're going to produce carbon dioxide and water. So what we're going to then have is those gases, and we can pass them through collection devices that are going to absorb one or the other. And then afterwards, we can measure to see how the mass has changed. And then based on the stoichiometry, based on the mass of water vapor, based on the mass of carbon dioxide, we can then figure out the mass of carbon and hydrogen in those original samples, and then get the empirical formula. So if you see it here, we've got our sample. We're passing oxygen through it because that's going to be necessary for the combustion reaction. But then in this right-hand side, we've got two different chambers. So one of them you can label the water absorber. One of them is going to be labeled the carbon dioxide absorber. Excuse me. So based on the absorbing substance, it'll either collect water or carbon dioxide. So if we pre-weigh these chambers and then weigh them again after the reaction, we're going to be able to get the mass by difference. And then based on the mass of water, based on the mass of carbon dioxide, we're going to be able to figure out the percent composition of carbon and hydrogen in that original sample, and ultimately get the empirical formula. If we have extra information, we could get the molecular formula. And then with this, you could do it with similar types of substances, but depending on what's being produced, you would just need a different absorbing substance in the collection devices. All right, so this one tells us polyethylene is a hydrocarbon polymer used to produce food storage and many other flexible plastic items. So with polymers, they're essentially just really long chains of repeating units. And with this sample, has a mass of 0.00126 grams. And the combustion of that sample produces 0.00394 grams of carbon dioxide and 0.00161 grams of water. We want to figure out what the empirical formula of this substance is going to be. So with it, again, we've got the mass of carbon dioxide. We're going to be able to do stoichiometry to then figure out how much carbon was going to be in that original sample. We've got the mass of water vapor produced. So again, we're going to be able to do stoichiometry to figure out how much hydrogen was in that original sample. And then based on the ratios of those two, we're going to be able to get the empirical formula. So if we just look at it here, again, we've got the mass of both of those. So the process here is going to be very similar. It's just going to be depending on which element, which gas we're starting with. So with carbon dioxide, that's going to give us carbon. Water, that's going to give us hydrogen. But in each case, we can take the mass of that component, divide it by the molar mass, and figure out how many moles of those substances we have. Then based on the balanced chemical reaction, or actually with this case, we don't need the chemical reaction here, so normally stoichiometric factors looking at the chemical reaction. But in this case, we're just going to think about it. For every 1 mole of carbon dioxide, we're going to get 1 mole of carbon. And then with the water vapor, for every 1 mole of water, we're going to get 2 moles of hydrogen. So then based on the moles we have there, we can get the mass. So we can get the percent composition from that piece. Or if we just stop with the moles here, we can get the mole-to-mole ratio, which will give us the empirical formula. So depending on exactly what we're looking for, with this type of analysis, we could get percent composition, or we could get the empirical formula. I mean, or both. So if we look at it here, again, very similar processes. We just got the different mass of those gases to start, the different molar masses on the bottom to give us moles of carbon dioxide or moles of water. And then with the carbon, since we get 1 carbon per carbon dioxide, that's just why it's 1 mole carbon on top. Whereas with the water, we get 2 hydrogens per water. So that's why we've got these 2 moles of hydrogen on top. But now we've got the moles of each of those substances in that sample. We're going to divide by the smaller one and see that we get a mole-to-mole ratio of 2 hydrogens for every 1 carbon. So our empirical formula then would just be CH2. So for every 1 carbon in polyethylene, there's going to be 2 hydrogens in that substance. If we had the molar mass, which with polymers, it's kind of just an average because the polymers themselves, like I said, are just really long repeating chains. So in some cases, the chain length actually differs. But if we had the molar mass, we could get the actual formula of the substance. But based on this information, we only know for every one carbon, there's going to be 2 hydrogens. And then that'll be the end of chapter 4. But remember, with all of the chapters, the textbook has the different sections broken up at the end. So you've got different questions based on the section, so you can kind of go and focus on anything in particular. And then there's also different practice assignments on campus too with the answer keys.